Transformer losses are the various forms of energy dissipation that occur in a transformer during its operation. These losses affect the efficiency of the transformer and result in energy being lost as heat, sound, or other forms. Losses in a transformer are typically categorized into two main groups: no-load losses, core losses, and load losses, copper losses. In electrical power systems, transformer extra losses by harmonics refer to additional losses in transformers caused by nonlinear loads that produce harmonic distortions in the power system. Harmonics are voltage or current waveforms at integer multiples of the fundamental frequency, e.g., 50 Hz or 60 Hz. Nonlinear devices, such as computers, variable speed drives, and other electronic equipment, often introduce these harmonics. Core losses, no-load losses. These losses occur even when the transformer is energized but not supplying any load. They are primarily due to the magnetic field in the transformer core. Core losses are divided into the following types: hysteresis losses, caused by the repeated magnetization and demagnetization of the core material as the alternating current passes through the transformer. Dependent on the material properties of the core and frequency of operation. Proportional to the area of the hysteresis loop of the core material. Eddy current losses. Induced currents. Eddy currents are generated in the transformer core due to the changing magnetic field. These currents circulate within the core and cause heat, leading to energy loss. Proportional to the square of the frequency and the thickness of the core laminations. Reduced by using laminated cores with thin sheets to minimize eddy currents. Copper losses. Load losses. These losses occur due to the resistance of the transformer windings when current flows through them, typically under load conditions. Copper losses vary with the load on the transformer. I2 are losses. Winding resistance losses, caused by the electrical resistance of the transformer windings. Proportional to the square of the current. I2 or vary with the load current. Higher loads result in higher copper losses. Stray losses. Losses caused by leakage flux. Magnetic flux that doesn't follow the intended path, linking with structural components such as the tank, windings, and other parts. These losses result in circulating currents and eddy currents in components other than the core. Stray losses in structural parts. Stray losses are a category of additional losses that occur in various parts of the transformer, especially when operating under harmonics or high currents. These include tank losses, losses due to eddy currents induced in the transformer tank or enclosure by the leakage flux. Clamping structure losses, losses due to the magnetic flux linking with the clamping structures that hold the transformer windings in place. Losses in winding conductors due to harmonics, caused by harmonic currents that flow in the windings. Harmonics lead to additional eddy currents and increased copper losses. I2R. Dielectric losses. These losses occur due to the presence of insulation materials between the windings and the core. The insulation material experiences energy loss when subjected to alternating voltage. Dielectric losses are proportional to the frequency and the applied voltage and depend on the quality of the insulating material used in the transformer. Mechanical losses. Vibration and noise. Mechanical losses are caused by the vibration of the transformer core and windings due to magnetic forces acting on them. Although they don't directly affect the electrical efficiency, they can lead to mechanical stress, resulting in wear and tear over time. Vibration losses. Vibration can occur due to magnetic forces within the transformer, leading to frictional energy loss. Noise losses. Noise, while typically not an energy loss, can indicate inefficient transformer operation due to core magnetostriction, a property of magnetic materials that causes them to change shape slightly when magnetized. Harmonic losses. Extra losses due to harmonics. In the presence of harmonic distortion from nonlinear loads, transformers experience additional losses beyond normal operation. These include increased copper losses due to harmonic currents. Harmonic currents increase the overall RMS current in the transformer, causing higher I2 or losses in the windings. Increased eddy current losses. Harmonics increase the frequency of the current flowing in the windings, resulting in higher eddy current losses in the transformer core. Increased hysteresis losses. Harmonics cause more frequent reversals of the magnetic field, leading to greater hysteresis losses in the core. Skin effect and proximity effect losses. Harmonic frequencies cause the current to concentrate near the surface of conductor's skin effect, increasing resistance and, hence, losses. Proximity effect occurs when currents in adjacent conductors affect each other, leading to further resistance and losses. Magnetizing current losses. Magnetizing current is the current required to establish the magnetic flux in the core. While this is generally small, any losses associated with magnetizing current are part of the overall core loss. Losses due to magnetizing current are mostly part of the core losses and are affected by harmonics. Load tap changer LTC losses. Transformers equipped with load tap changers LTC to adjust voltage under load will experience additional losses due to the presence of moving parts, contact resistance, and transition currents. Cooling system losses. If the transformer is equipped with an active cooling system, such as oil pumps or cooling fans, these auxiliary components contribute to overall transformer losses. Fan and pump losses. Electrical losses from fans and pumps used to cool oil or air in larger transformers. These harmonics can cause significant extra losses in transformers due to a few key mechanisms. Increased copper I2R losses. The winding resistance of a transformer leads to power loss, proportional to the square of the current I2R losses. Harmonic currents increase the overall current flowing through the transformer windings. Since these harmonics are at higher frequencies, the magnitude of current drawn is higher for certain harmonic orders, which in turn leads to greater copper losses. Increased eddy current losses. Eddy currents are induced within the transformer's core and windings due to the changing magnetic field caused by current flow. Harmonic components in the current cause rapid changes in the magnetic field, which induce larger eddy currents. Eddy current losses increase with the square of the frequency, meaning that higher order harmonics such as fifth, seventh, etc. produce significantly more eddy current losses than the fundamental frequency. Hysteresis losses occur in the transformer core as the magnetic field reverses direction with each cycle of the AC supply. Harmonics cause more frequent changes in the magnetic field, leading to additional hysteresis losses. Since these losses are dependent on the magnetic properties of the core material, higher frequency harmonics exacerbate this problem. Skin effect and proximity effect. At higher frequencies as present in harmonics, the skin effect causes current to be concentrated at the surface of the conductors, effectively reducing the cross-sectional area available for current flow. This increases the effective resistance of the transformer windings. Additionally, the proximity effect causes current distortion in closely spaced conductors, further increasing resistance. Both these effects lead to higher losses in the windings at harmonic frequencies. Magnetic saturation. Harmonic currents can push the transformer core into saturation, especially third-order harmonics and their multiples called triplen harmonics. In saturation, the core is less efficient at conducting magnetic flux, leading to overheating and increased losses. Mitigation of harmonic losses. To reduce the impact of harmonic losses in transformers, power system operators can use harmonic filters to reduce the amount of harmonic distortion in the system. Install transformers specifically designed to handle harmonic-rich environments, such as K-rated transformers. Implement active power conditioning or compensation systems to maintain power quality. In your role as a power system operator, understanding these losses is essential for maintaining system efficiency and transformer longevity. By controlling harmonics, you help reduce the extra losses and avoid overheating, increased maintenance, or even transformer failure. Harmonic frequencies and their impact on transformer losses. Harmonics are generated as multiples of the fundamental frequency, e.g., 50 Hz or 60 Hz, and their behavior affects transformers differently. Second harmonic 120 Hz or 100 Hz, introduced by certain types of electrical devices but less common in typical industrial loads. Third harmonic 180 Hz or 150 Hz, generated by single-phase loads like computers, lighting ballasts, and UPS systems. The third harmonic is particularly troublesome as it is a triplen harmonic and adds up in the neutral conductor, leading to neutral overloading in three-phase systems. In transformers, it contributes heavily to core saturation and stray losses. Fifth and seventh harmonics 300 Hz, 420 Hz, or 250 Hz, 350 Hz, typically generated by variable frequency drives VFDs, rectifiers, and other industrial equipment. These higher-order harmonics cause significant eddy current and skin effect losses. Higher-order harmonics, while smaller in magnitude, have more pronounced effects due to their higher frequencies, resulting in disproportionate eddy current and hysteresis losses. Stray losses in transformer components. Apart from copper and core losses, stray losses in other transformer components are amplified by harmonics, tank losses. Harmonics induce eddy currents in the transformer tank itself, which can lead to significant heating and localized losses. Clamping structures and windings. Harmonics also induce currents in non-conductive parts of the transformer structure, leading to additional stray losses. These losses tend to increase rapidly with harmonic frequency, making them critical in high-frequency environments. Harmonic heating and thermal effects. Due to the extra losses caused by harmonics, transformers experience excessive heat generation. This heating is unevenly distributed in the transformer components, hotspots and windings caused by skin and proximity effects. Core overheating due to increased hysteresis and eddy current losses. Over time, this heat can lead to insulation degradation, reducing transformer lifespan and reliability. Moreover, if harmonic distortion remains unchecked, it may cause a transformer to operate well beyond its design temperature rise limits, further accelerating wear and tear. Losses due to non-sinusoidal flux. The presence of harmonics alters the magnetic flux waveform inside the transformer core. Transformers are designed for sinusoidal flux at the fundamental frequency, but harmonics produce non-sinusoidal flux. This results in harmonic flux, which causes additional core losses. Core saturation, especially from low-order harmonics such as the third harmonic, which induces severe magnetizing current and heat buildup. Non-sinusoidal flux also increases vibration and noise levels, contributing to mechanical stress on the transformer structure. Harmonic resonance. In complex power systems, transformers can encounter harmonic resonance, a condition where the inductance and capacitance of the system resonate at a harmonic frequency. When this occurs, the harmonic currents at the resonant frequency can increase exponentially, leading to even greater losses in transformers and other system components.